I'll continue the column stability. Firstly, I'll cover this the special column. This column has two P, and this column has the different I1 and I2. This column has the two-story column. For this two-story column, I present PCR K. The meaning to get the PCR and K, that means this analysis is bifurcation analysis, right? Secondly, I'll cover the initially crooked column. We already learned eccentric loaded column, okay, before. So today, I will present initially crooked column. In that case, we have to do load deflection analysis, right? Lastly, I'll present inelastic column. So far, you learned regarding PCR. It is elastic column. That means pi square EI, this E is elastic, so L square. So in elastic column, there are two different inelastic column, PT, PR. This E is not anymore elastic range. So in elastic range, I'll cover these three different issues. Let's look at that this kind of some continuous member subjected to axial force. So this member is column, although it lies horizontally, but this member subjected to axial force. This member is column, so two-story column. The length is 1.5 L and L. So far we learned just this kind of a simple one-story column, but this one is two-story column. In this column, we will get PCR and K, buckling load and K, effective length factor. In order to get the PCR, we have to do bifurcation analysis, right? Or eigenvalue analysis. Firstly, use first order method. Do you remember first order method? In first order method, the governing equation is this, right? Y per prime k square y1 prime. Okay. Last lecture we already derived this equation, right? So the coordinate system in left-hand side member, we have x1, okay, this direction, and then y1, this direction. And then right-hand side member, for this member, we have another coordinate, different coordinate, independent coordinate. X2, that direction, Y2, upper direction. Okay? So we have two different coordinates. In order to solve this problem easily, so we use different coordinate. Before going through this equation, we have to determine sign convention. To understand, let's look at the sign here, theta 1 and theta 2. This can be used for later for continuity condition. Let's look at theta 1 first. We start here. We have to go this way. This x1 direction is right hand side, but this way is left hand side. So minus dx1. Okay? And then downward, minus dy1. That is theta 1. So tangent theta 1, this angle equal minus dx1 minus dy1 is plus sign. Okay? We have to determine the sign convention firstly. Here, tangent theta 2, that is, it start this point, this direction, and upper direction. So right hand side, but x coordinate is left hand side is plus. This one is right hand side, so minus dx2 about dy2. Tangent theta 2 equal minus dx2 dy2. So it is minus. Do you understand? Another sign convention is this. Look at here. We assume the moment direction like that. This direction and this direction. Moment direction. So if we establish the equilibrium at this point, that is clockwise, counterclockwise, m1 minus m2 equals 0. It is the moment equilibrium at this joint. So m1 equal m2. If we consider sign convention, this m1 and m2 equal minus ei y2 prime. As x increase, the rate of slope decrease. So minus ei y2 prime. This also same. X increase, the rate of slope decrease. So minus EIY2 prime. That is sign convention for this fourth order differential equation. Yeah, so governing equation is this one for left hand side member. Yeah, segment 1. Solution is y1 equal a sine kx1 plus b cosine kx1 plus c x1 plus d for fourth order differential equation. Do you remember? We already learned this one. Okay. Let's look at the right hand side member. We use coordinate x2 y2. So the governing equation is this one. y2 4 prime plus k square y2 2 prime equal 0 for segment 2. So the general solution is y2 equal e sine kx2 plus f cosine kx2 plus gx2 plus h. So we have 1, 2, 3, 4 unknown, and we have another 4 unknown, e, f, g, h. So in order to solve this problem, we have to have totally 8 equations. This 4 and 4, then 8 equation. So we will establish those equations using boundary condition and continuity condition. So in boundary condition, as you see here, the displacement here equal 0. So y1 0 equal 0. And how about moment here? Moment equal 0, right? ei y1 2 prime equal moment, right? So ei is not 0. y1 2 prime must be 0. And then how about this location? The support location is 0, right? So y1 1.5 L, this location equals 0, right? Right hand side segment 2, y2 0, this location, displacement is 0, right? The moment, this point is 0, okay? Displacement, this location equal 0. So you have 6 equations using 6 boundary condition. Then you need 2 more equations. How to make it? You can make using the continuity condition. What continuity? As you see, the slope here is identical. So theta 1, theta 2 identical. But what is different? Sign is plus minus. So from some the coordinate x1, y1, the continuity, some slope here equal y1 prime 3 over 2l. That is slope from segment 1. From segment 2, you have slope y2 prime l. This location is l. The sign is plus or minus, so minus sign should be used. How about the moment here? The moment is identical. So from segment 1, y2 prime 3 over 2l equal y2 prime l must be identical from here. Okay, that is continuity condition. These two equations are continuity conditions. You must know EIY equal moment, right? EI can be cancelled out. Then remaining term is this one. Using these 8 equations, you can get the BDFH equal 0. If we input this condition here, y1, y2, then you can get this equation. And then you have the additional 4 equations can be written in this matrix form regarding A, C, E, G. So this matrix form. So in order to satisfy the 0, this equation, this determinant must be 0. If you take the determinant from here, you can get this equation. 5 sine 3 over KL sine KL minus 3 KL sine 3 over 2 KL equals 0. From this equation, you can get the K value. How to get the K value? By trial and error approach. Do you know how many solutions of K exist? How many K satisfy this equation? How many? Infinite number. Why? As you see, this one is deformable column. So degree of freedom of this column is infinite. So the solution regarding K is infinite. From K, we can calculate PCR. Okay, bucket load. Infinite number of critical load due to the infinite degree of freedom. By trial and error procedure, you input the KL value. Let's say like that. You input 1 for KL, okay, and 2, and check. this equation is 0. If we input 2 and nextly input 3, between 2, the sign is changed. Yeah, this value is change, plus minus. Then you can realize, oh, the solution must be 2 and 3, like that. Use that kind of trial and error procedure. You can finally get KL equal 2.427. Okay, so K equal 2.427 of L. So as you know, K square equal PEI. So PCR is K square EI. It is K equal this one. Okay, K square 2.427 square is 5.89 EI over L square. So you get the minimum critical value, buckling load of what? This two-story column. If P reach this value, then this column suddenly buckle like that. Now let's calculate the K factor. Do you remember K factor equal square root to PE over PCR, right? The minimum PCR is just 1, but this K factor, you can calculate segment 1 and segment 2 separately. You have a unique PCR, I mean the minimum critical load for this column, but K factor exists too. Segment 1 has its own K factor, segment 2 has its own K factor. So you can calculate K1 for segment 1 equal PE PCR. PCR is unique value. Okay. PE, Euler buckling load. If you consider this column only, if we ignore right hand side, simply support the column case, the P equal pi square EI over L square, but this L is 1.5 L. You use this value, then you can get 0.863. Let's look at K2, this segment 2, square root 2 P PCR, input like that, then you get 1.294. So each segment has its own K factor like that. If you look at this figure, this length is short, this length is long. So long column is weak basically, right? Do you agree? The PCR is smaller than short column. So long column is weak column. Short column is a strong column. But when you calculate the K factor of this long column, weak column is 0.863, less than 1. This strong column K factor is 1.294, greater than 1. So what happened in this column? Do you remember, if K factor is less than 1, if K value is small, that means the column is strong, right? If K value is larger than this one, the column is weak. Yeah. But originally, this segment 1 is weak column, segment 2 is strong column. But result is something strange. K1 is strong, K2 is weak. Okay? What happened? You know, they are connected. So this the phenomenon here is this strong column help weak column. That means strong column prevent the buckling of weak column. So in another the way, we can express like this. Weak column gets some help from strong column. If they are independent, this weak column K must be 1.0. This short column also K equal 1.0. But they are connected, so they are correlated. How to correlate? This short column help weak column. I mean the strong column help weak column. Okay, weak column gets some help from strong column. So we call it leaning effect. So weak column leaning on strong column. This is inflection point. That is leaning effect. Let's look at the second order procedure. Here P, the coordinate is identical. Then a free body diagram like this. M internal is minus EI, Y2 prime. Why? this one is again minus EI y2 prime. So now using the second order method, solve the same problem. Establish the equilibrium, then minus internal plus py equals 0. This one is minus m internal py2 equals 0. And then you can rewrite the equation like this. You can have some general solution for segment 1. Okay, y1 equal like this, y2 equal like this. Okay, so in order to solve this problem, you have 1, 2, 3, 4. No. Okay, you need the 4 equation. Boundary condition y1 0 here, displacement 0 here, displacement equal 0. Then we will use the continuity condition here. So y1 1.5L, the slope here and slope here, the sign like this, minus sign, right? And then moment here and moment here, this point from different coordinate must be identical. If you solve using this boundary condition, you can get the same PCR like this. Okay, same K1 and K2. Okay, you can solve by yourself because it is a limited time. Okay. Next topic is that the initially crooked column. As you see, this column has the initial deformation before the actual force apply. So we called it initially crooked column. The maximum value is delta 0. And then if you apply the load, the displacement increase like that. So you can take out the free body diagram here. P, initial deformation y0 at this point, and then y displacement due to P. So you have m internal moment equal minus EI y2 prime. So we are doing the bifurcation analysis or load deflection analysis for this problem. Initially crooked column. Yes, we are doing load displacement analysis. That means as load increase, displacement increase. So it is load deflection analysis. So we have to assume initially deformed shape y0 equal delta 0 sine pi over Lx. The maximum deformation equal delta 0. This curve is a sine curve like that. Sine pi over Lx like that. We assume like this. Then we establish the equilibrium equation minus m internal p y0y equal 0. Right? So m internal equal EI y2 prime. If you let k square equal p over EI, you can rewrite y2 prime k square y, right? And then k square y0. And then you move left hand side. Then minus k square, right? What is y0? Delta 0 sine pi over Lx. Initial deformed shape. Then we have to solve this differential equation. If we let this left hand side equation equal to 0, then you can get the homogeneous solution. YH equal A sine kx plus B cosine kx. And then you have to input some value here. Then you have to find some particular solution to get this equation. By investigation, this right hand side sine curve of this type, we can assign particular solution equal c sine pi xl d cosine pi xl. That is general, the particular solution. And then you input this value here, left hand side, then must be equal to right hand side. So let's input this value here. You have to take second derivative. If you take second derivative, then you get pi square L square like that. And then here y, you input again here. Then you can get this, the equation. C sine pi square L square k square delta 0 sine d, something like that. In this equation, this right hand side, this k square delta 0 sine pi x square, we move it to left hand side and rearrange like that. Okay, so in order to satisfy the 0, that means this one must be 0, right? And then this one also must be 0. From this one, equal to 0, you can get C value, minus K square, like this. If you replace K square equal EIP like that, then you can rewrite equation like this. And then this must be 0. That means D0 or this one equal 0, right? D equal 0 or this one equal 0 means K square equal pi square L square. So from this equation you get PE Euler-Bucking load. Euler-Bucking load is for bifurcation analysis. Our problem is low deflection analysis. So this is not appropriate solution. That means T equals 0, right? So finally you can get this D equals 0. You have a C value, this value. So this homogeneous solution, this C and sine pi XL. Yeah, this is general solution. Now you have two unknown A and B, so you need two equations. So boundary condition, displacement at the bottom equals 0, top equals 0, right? So y0, 0, yl 0. From this equation, B equals 0. If we input 0, 0, then this is the deleted. YL equal A sine KL. Yeah, because of B0, if we input the L here, sine pi equals 0. Okay, so A sine KL equals 0. So here, A equals 0 or sine KL equals 0. Sine KL equals 0. From this equation, you can get P equal PE. So this is not the solution because this problem is low deflection analysis. But P equal PE equal bifurcation on the solution. A must be 0. So this 0, this 0. B0. So remaining one is this one. So y equal the solution. We get solution like this. So let's calculate y total. What is y total? Initial deformation and the displacement due to P, second order displacement. So if we add together, so do you remember y0 is delta 0 sine pi over Lx, right? So add together, then you can get this equation. Okay, you can make this equation simple as this. Yeah. So if you investigate this one is a first order deflection, right? Deformed shape. We assume like this, right? And then this term is amplification factor. So this total is second order deflection. First order deflection times amplification factor. Delta maximum occurs at mid height of the column. If you see delta maximum here, that means x equal L over 2. If we input L over 2 equal, this is 1. So delta maximum is this one. So let's calculate moment. Second order moment equal P times deformation. This moment equal P times y0 plus y. That is moment. P times y plus y0. Y plus y0. What is that? Y total. What is y total? This is y total. P times delta sine, like that. This is first order moment. The deformation times P. That is first order moment. Amplification factor here. So this one is second order moment. If we draw this curve regarding P over PL and amplification factor, then we did initially crooked column. Okay, some amplification factor is like this: 1 over 1 minus P over P. This one, right? Do you remember the eccentrically loaded column? We already learned. At that time, what is the amplification factor? Is this one. Do you remember? Secant pi over 2 square root of P over PE. If we draw this one also, they curve like this. Yeah, they are very similar. If we draw P over PE, P increase from 0 to PE. Then we can draw delta maximum over L. Initial deformation equal the ratio of L equal if 0.005, we can draw a curve like this. If we have a little smaller value, we can have this curve. See you again, everybody.